Now, let's understand an unsigned integer for n bits. N bits unsigned integer. Okay? So we start from bit 0 on the right, and it also represents the LSB, just like what you already learned, base 2 number, and x n minus 1, which is the most significant bit. Okay? For how many bits? Totally n bits, from 0 to n minus 1. That's what you already learned. I put it in officially. So how to compute to get its base 10 number? You basically multiply its positional value. For example, x0 multiply with 2 to the 0. x1 multiply with 2 to the 1. xn minus 1 multiply with 2 to the n minus 1. That's what you already learned. Okay? And I called it capital X sub 10 U. U is unsigned. 10 is base 10. Okay? Let's take a look at this example. X base 2 is 1 0 1 1 base 2, which is B base 16. Okay? Which is what? In base 10? 11. Because you know that A is 10. B is 11. But now, I would like to show you that for 1 0 1 1 base 2, you can compute to get base 10 number like this: 8 plus 0 plus 2 plus 1, which is 11 base 10. Okay? Any question? Very straightforward. Because we interpret this as unsigned. Okay? Now, let's make it even backward. We want to convert base 10 to base 2. How? You have two methods. Method number 1 is division method. You see that? This is called division. Okay? Method number 2 is on the next slide. It's called subtraction method. Ready? Division method is so easy. You already learned. How about subtraction method? You may not have learned. Okay? Let me explain the second method. Convert 123 base 10 to something base 2. For how long? For 8 bits long. For 8 bits. Okay? Therefore, when n equals 8, oh, by the way, we look at this as unsigned. Okay, unsigned base 10. Keep in mind, this number is unsigned. Okay, for 8 bits, we start with bit number 7, bit number 6, 5, 4, 3, 2, 1, bit 0, all the way to 0. So the positional value, remember, 2 to the 7, 2 to the 6, 2 to the 5, all the way to 2 to the 0, you get 128, 64, 32, 16, ... Now, we put 123 to subtract with the positional value of bit 7, which is 128. So 122 subtract 128, is it going to work? No. So it's not subtractable. So we put 0. The remainder is still 123. Now the 123 is subtracted with 64 again. Is it subtractable? Yes. So we put 1. What is the remainder? 59. So put 59, subtract the positional value of bit 5. You get subtractable? Yes. Remainder is 27. Okay? We can continue until the remainder is 0. Therefore, it's 0, 1, 1, 1, 1, 0, 1, 1, base 2. This is 123 base 10. Are we cool? In other words, you can visualize it as 64 plus 32 plus 16 plus 8 plus 2 plus 1. Cool? Are we cool? Or you can visualize it as 127 subtract 4 equals to 123. What is 127 base 10? 0, 1, 1, 1, 1, 1, 1, 1, base 2. Subtract 4. What does it mean, subtract 4 base 10? Look at the screen. Subtract 4. That means this bit becomes 0. You always do this, right? No, this is a tricky method. Much faster than the original method. Subtract 4. Done. Here. Bit 2 to the 2 is 0. That corresponds to subtract 4. I always do the same thing because this is tricky. This is much faster. Any number you can come up in 8 bits with 8 bits long. For example, 65. 65 is 64 plus 1. Right? 64 plus 1. What is 64? 64 is 63 plus 1 again. So what is 63? 63 is 0, 0, 1, 1, 1, 1, 1, 1. Right? This is 128. This is 64. This is 32. Oops. No. I put the wrong 64. This is 32. This is 16. Right? So 63 is 32 plus 16 plus 8 plus 4 plus 2 plus 1. That's 63. Plus 1 more. And plus 1 more, you will get 65, right? So you add 1 more, you get 0, 1, 0, 0, 0, 0, 0. You add 1 more, you get 0, 1, 0, 0, 0, 0, 0, 1. Which is 64 plus 1 here. Okay? So it's tricky if you can recognize this bit as 64. Much faster. Okay.